Good morning, everyone, or good afternoon if you're in Europe. So welcome to today's session of the Cultural Seminar. It's my great pleasure to introduce Samaria Montenegro from Universidad de Costa Rica, and she will speak about groups definable in partial differential fields with an automorphism.
Thank you so much, and thank you for the invitation. So, as Ronnie says, I always speak about a group definable in partial differential fields with an automorphism, and this is a joint work with Ronald Bustamante Medina. He is also from the University of Costa Rica, and with Zoe Chatzirakis, who is from Paris, the École Normale of Paris, and CNRS. So the idea is that this is a talk in model theory. I want to study what happened with definable groups who are in fact definable is in fields that has finally many derivations and also an automorphism. So I will give you just some quickly definitions. So you already know that the fields with operators are really important. So even if you have derivations or an automorphism and appear everywhere in mathematics, in particular in areas who are close to algebra. The study of differential and difference fields has been important since the 14th or maybe before that, and has many applications in area of mathematics. And a lot of people works in that, but for example, the development of differential and difference algebra that backs from, I'm not sure of the that, but to reach in the 50s and was also expanded by Kolchin and by Kohn and by a lot of people in the 60s. So I will give you quickly some definitions to be sure that we are all in the same page. So I will work with finally many derivations. So we will take delta and set with delta and delta m will be the derivation. And when I say that I work with a delta field, I will suppose all the derivations are commuting, okay? We take the rings of polynomials. The notation that I will use, that will be this one. So this is the rings of polynomials, of differential polynomials. That means that our variables that will be combinations of powers of delta and the usual variables. And the element that will be differential polynomials or delta polynomial if you want. And of course, you know that we have a topology that comes from these delta polynomials, and the topology are called the Kolchin topology. It's a really nice topology, in particular it's Noetherian. And there are important fields when I have, and delta fields that are important fields that I will use. And in fact, they are really important because they are definable. And that will be the fields of constants. So suppose that we have delta, your set of derivations, and delta prime that will be a subset of delta. So a field of constant that will be the elements of the fields such that delta x is equal to 0 for all derivation in delta prime. So if you only have one derivation, so you will have a field of constant, and if you have a lot of derivations, so you will have finally many fields of constants. Okay. What we know in the sense of model theory of these fields, okay? So I want to work in these fields, but in the sense of model theory. So I need to be sure in what language I am working. So I will take the language of rings and I will use symbols for any derivations. So I will take delta, the set of the derivations, and that will be in our language. And I will work in the language of rings with the delta. We want to study these fields, the differential fields in the sense of model theory. So in the case of only one derivations in characteristic 0, this is important, I am only working characteristic 0 here. So in the case of m equal 1, the work was started by Abraham Robinson and by Leonard Bloom in the sense of model theory. And in the general case, that is the case that I am interested, that was proved by Tracy McBride, that the model companion of the L delta theory of differential fields of characteristic 0 with m commuting derivation exists, okay? And this model companion that will denote by DCFM, okay? So in that case, we are working with fields with m commuting derivation, and we know that the model companion exists, okay? What we know about this model companion. So we know that this is a really nice theory in the sense of model theory, the L delta theory of DCFM. We know that it's complete. eliminates quantifiers, of course, in the language with the derivations. So that means the definable sets are really nice, are just equations, the differential equations, some Boolean combination of that. We know that eliminates imaginaries, and we know there is omega stable. So in model theory, because I'm not sure that I suppose that there are not only people of model theory here. So in model theory, that means that the theory is really nice. So that have all the good properties that we know on model theory. In particular, we have a good notion of dimension, and everything works really nice. So it's the best that we can have in model theory. The fact that the theory is stable, we don't have a lot of types, etc. And we also have that has a unique prime model. And the models of this theory are called differentially closed. Okay, so this is really nice. We have a good notion of, we have a good theory in the sense of model theory, but I am interested in understand what happened with the definable groups in general.
Question, what is a prime model?
It's a model that embeds in any model. So it's kind of the little model, the most little model that we can have. In any case, that is just some properties general that we know in this theory, and the models are called differentially closed. So in particular, the models has this property. Remember that differentially closed fields are the model companion of the theory of differential fields. So in particular, that means that they are existentially closed in the language with the derivation. So that means that if you know that there exists a solution in some extension, in particular a solution for a system of differential equations, so you have the solution in your field, okay? And what do we know about definable groups in these fields? So this is in fact the inspiration of our work that was proved by Cassidy. I think that Cassidy was a student from coaching, but I'm not completely sure. So she studied, so Ronnie says yes, so it's true. So she studied definable groups in this context in differentially closed fields with commuting derivations. So what she proved? She proved though, so you take a monster model of differentially closed fields, that means that is a big model of differentially closed fields. And you take, she will start definable groups inside a simple algebraic group. So you take a simple algebraic group, you allow finite center. So you take a simple algebraic group who is simple algebraic in the sense of algebraic, and you take a definable subgroup who is inside H of U, the rational points of H. Okay. So the idea is that we want to understand definable groups inside a simple algebraic group, and suppose also that G that would be Zarinsky dense in H. So what she proved? She proved that in fact G is really similar to the rational points of H of L for some L that will be a definable field, but in particular that will be a constant field of a set of commuting derivations. So what that means? So you take your G, who is inside definable inside a simple group, and you prove that in fact this G that will be really similar because they will be isomorphic, and in particular the isomorphism is given by a conjugation of the rational point of H of L, and this L there will be a constant field of our field. So in particular, it's definable in the language with derivation. So the idea is that we want to generalize this result, but now in the context that we not only have derivation, but we also have an automorphism. And when you have an automorphism, the things can be a little bit more complicated, because in particular, the theory with one automorphism in the sense of model theory is a little bit more complicated. That indicates that you only have derivations. So I will speak a little bit about what happened and what we know in the case that we only have one automorphism, and then we can put the things together. So
may I ask a question, please, about the theorem?
Yeah.
So the delta prime is a subset of the original delta, right?
No, that will be in fact Boolean combination of delta. That will be a set that is constructed about Boolean combination of our original delta. So for example, that can be 2 delta 1 plus 3 delta 2, for example, something like that.
So it may be linear combination.
Yeah.
Linear. Okay.
Yeah.
Thank you.
I will say that this theorem of Cassidy in the paper of Cassidy is not given in that language. It's given in another context. It's exactly the same. So I put the traduction in our sense, but she speaks about Lie algebra and Chevalier groups, and it's a statement in a different way. But this is the traduction for our context. Okay. So what we know indicates that we have only one automorphism. So these are the different fields, and we have the same. We have the ring of polynomials, and the elements of this ring of polynomials are called sigma polynomials. And this is exactly the same. We will have also a topology that will be also a Noetherian topology, so a nice topology. And we have important fields in this context, and that will be the fixed field. Important thing is that maybe you can ask what happens if you not only have one automorphism, that you can have maybe finally many automorphisms. Yes, you can do the same. So if you have sigma 1, sigma 2, sigma n automorphism that commutes, so you will have also the ring of polynomial, you will have also a topology that will be also Noetherian, and so that you will have different fixed fields that comes from the powers and the combination of the sigma. But why I am more interested in the case that one is because the model theory, when you have a more automorphism, is a little bit more complicated. So maybe we can speak about that later. What we know of the theory that we only have one automorphism, we know that the model companion exists, and the name that would be ACFA. Okay. What we know about this theory is also model complete, that will be not stable. So it's a little bit more complicated. In model theory, you have this universe of Shella that told us where if the theory is more complicated or no, and we have good properties or not. So stable are the best properties. So super sample are a little bit more complicated, that are stable, but in any case are really nice. So you know that the forking is nice and everything works more or less nice. We also have that eliminates imaginaries, but it's not complete. So in fact, it's not complete. That means that when I say super sample, it's not true. So every completion is super sample. So it's not complete. Do not eliminate quantifiers. And the problem is that you can extend maybe the automorphism to the, if you have an automorphism from a field, maybe you can extend to the algebraic closure in different ways, not in an only way. So this is why you have different different completions, but we understand the completions, and all the completions are obtained by describing the isomorphism type of the difference of fields of the algebraic closure of Q, or in the case of characteristic P, of the algebraic closure of FP. So in any case, that means that the model theory is really nice, and we understand what happened. So what happened, we aren't interested in study definable groups in this context. What we know, if you don't have derivation, that you have an automorphism. That was a theorem that was proved by Chatzirakis, Hushowski, and Peterson. This is exactly as the Cassidy results. It's really a version of the Cassidy results, but for this context, in the context that you only have one automorphism. So you take H, our simple algebraic group, exactly the same way, and you take a group who is definable inside the same idea, inside of H of U, who is Arensky dense. So they prove that they are definable isomorphic to one subgroup of this field. I am only interested in the case of characteristic 0, so you can forgive Frobenius. And the idea is that that will be isomorphic to H of fixed of some power of sigma. So again, and the isomorphic that will be also given by a conjugation. So the idea is that in fact, our definable group is really similar to the rational points of our simple groups, but now the rational points of some particular field, then now that will be the fix of some power of sigma, okay? So the idea is that we want to put all these two results together because we want to work in fields that has now derivations and also an automorphism. So I will go maybe a little bit, I will explain you a little bit what we know about this theory. So that would be the theory of differentially closed fields with derivation and also with an automorphism. So we want to mix derivation and automorphism. You take the derivation and you take an automorphism, and you will suppose that everyone commutes, okay? So you have an automorphism that commutes with all the derivations, and all the derivations commute. and when everything is fine, we will say that this is a delta sigma field. Again, you can consider finally many derivation if you finally many automorphisms if you want, and you can suppose that all the automorphisms commute, but it's a little bit more complicated, and in particular, when you have finally many automorphisms, the model companion doesn't exist. You can work in the class that is existentially closed, but it's a little bit more complicated. So for now, I will suppose that we only have one automorphism, okay? So again, you have a nice notion of differentially difference polynomials. that will be also nice, and the topology that comes is really nice. That will be a topology who is also Noetherian. So everything here is nice. What we know in the sense of model theory, we know that there exists a model companion. And for the case of m equal to 1, that means that you only have one derivation and one automorphism. That was shown by Bustamante in 2006. That was in fact his work in PhD. And in the general case, that was shown by Leon Sanchez in 2016. And if I am not completely sure, but I think that the strategy of Bustamante for the case of only one derivation is completely different than the strategy that used Leon Sanchez in the general case. Okay, what we know about this theory, we know that this theory is really nice. In fact, of course, it's not stable because now we have an automorphism, but we know that it's model complete. We know that each completion that will be also super sample because of course it's not complete. And we know that eliminates imaginaries. Of course, we don't have quantifier elimination because now we have an automorphism, but it's exactly the same thing that we know about, exactly the same that happened with only one automorphism. And the completions are obtained by describing isomorphism time of the differential fields. But in any case, even if we don't have quantifier elimination, we understand what happened with the definable sets. So suppose that you have a formula here. So you know that this formula, that will be a disjunction of formula who are of this kind of form, when this will be a quantifier-free formula. We can suppose that it's positive if you want. And in particular, that if this is true, so that implies that that would be algebraic over the first coordinates. So even if you don't have quantifier elimination, you know how are the definable sets and are just existential stuff of some formulas who are in fact defined only by differential polynomials. So it's nice. Other model theoretic properties. So you know that the algebraic closure in the sense of model theory is nice, and that coincides with the algebraic closure in the sense of algebra. That means the algebraic closure. That means that will be the algebraic closure of the differential field generated by A. Okay. We understand the types, so we know that the type of A is equal to the type of B. If you can find a sigma delta isomorphism between the algebraic closure of AA and the algebraic closure of AB that sends A to B. So we really understand what happened. We know that the independence is given by the independence in the sense of algebraic closed sets. That means A, B are independent over C if and only if the algebraic the fields who are generated by the algebraic closure are linearly disjoint. And this is a nice property that in fact we use a lot. If you take a model of this theory and differentially closed fields for that context, and you change your automorphism for another power of another, you take the same automorphism, but you change for a power of this automorphism, that will be also a model of DCFMA. And also, an important thing is the models of this theory are algebraic closed in the sense of algebra. So the algebraic closure of the Fico sigma, that will be a model of DCFM in the case that you only have derivations. So this is a nice properties that we use a lot. So what is the idea? Now we understand a little bit what happened with the model theory of in this context that we have derivation and automorphism. We want to put all together and have something similar to the Cassidy result. So we will use in the proof the same idea from the case of indicate that we only have one automorphism. we use something that they call the prolongations, but now in our context. So I will just recall a little bit that. This is the same that happened in the case that you only have one automorphism. You take a monster model of DCFMA, you take an algebraic group and H, and you can define a new group for each n. That will be the product. And I will put this name. So H of n, that will be the product of H of u, product sigma H of u, and you stop in sigma n H of u. Then that will be a new group. And you will take P of n, the group of homomorphism, that it's the thing that we think. So you take your element of the group and you send it so to the tuple of G sigma n of G. Okay. So we have that the image from H that will be Cauchy dense, in fact, in H of n. Okay. This is, remember that for that, each that will be an algebraic group. So now what happened if we take a definable subgroup of this algebraic group? So I will take G of n, the Cauchy closure of the image of G, that will be in particular L delta definable. So this G that will be definable by sigma and by delta because L is definable in our model of DCFMA. But now you take the image of G for this automorphism, for this P of n, and I will see this inside the product of H, and I will take the Cauchy closure of this. Okay, so in particular, that will be only defined by a different equation. So that will be L delta definable. And now I will take G of n tilde, that will be the element of G of the elements of the H of u, such that the tuple that will be is in G of n. Okay, and so that the G of n tilde, that will form a decreasing sequence of quantifier-free L delta sigma definable subgroup of H of u. But remember that we know that this topology, the topology that comes from the delta sigma polynomials are noetherian. So that means that the intersection of G of n tilde, that will be some G of n, okay? And in particular, that will be the sigma delta closure of that, okay? So you have a good correspondence between the generics of the groups and the generics of this in the other side. So that means that a generic in the group that will be equal, G is a generic of the group if and only if for each n, Pn of G, that will be a generic of the delta closed subgroup G of n of H of n. So, and in particular, we will have that G will have finite index in the sigma delta closure. So we will use that in the proof of the general theorem. So this is why I called you, I want to explain you a little bit that, but this is exactly the same idea that Chatzireski, Hrushevsky, and Peterson use from the case, and that you only have one automorphism. Yes?
Excuse me. This M is not the same as the number of derivations.
No, you are right. Sure. No, I can do that for each n. So this is a generic n. Yeah, you're right. Maybe it's not a good idea to use the same n. Yeah. Okay. So what is the theorem that we want to prove? What is our theorem? So now this is the principal theorem for that context. So this is the generalization of the theorem from Cassidy and from Hrushevsky, Chatzirakis, and Peterson. So you take a monster model of the CFMA, you take a simple algebraic group, define it over the rational, and you take a definable subgroup of H of u, who is an incidence inside of H of u. So it's same hypothesis, okay? What we obtain? We obtain that you can find a big part of G. So finite index and subgroup of G who will be big, no in particular have finite index. So here the problem is that we need to go to maybe the subgroup connected. So this is why we cannot say that for G. And we prove that in fact, but it's the same idea, but now with G0. So we prove that in fact, the Cauchy closure of G0, that will be isomorphic to H of L, and this L that will be a constant field, in particular definable field in the sense of derivation. And also we have two possibilities. So the conjugation, the same conjugation of G0 that will be in fact equal to H of L, or that will be a subgroup of, and now we have this, it's the same idea because we are mixing the two theorems, But the idea that will be a subgroup of the rational point of H, but now our field that will be L, that was the differential field, intersection with some power of sigma, okay? So in the later case, so in the case that we have, this, we obtain that we know exactly how is the conjugation of G0. So we know how to define that. So in the case that in the later case, if H doesn't have a center, because remember that if I am working with simple group, I allow center finite center. So we know that G0 of G, that would be the set of G of H of L, who are definable for this formula. So there will be some power of sigma in the left side, and in the right side, we only have a phi that will be only algebraic. So it's an algebraic automorphism between H of L and H of L. So doesn't have the derivations, okay? So we have, but in L, you have the derivation. Here you have your sigma, and in the right side, you can suppose that you have just an algebraic automorphism, okay? So maybe in the second part, I will give you a sketch of this theorem, but the idea, the general idea is that we want to put together, we use the Cassidy result in the first, and then we do the same strategy for the case that we only have one automorphism, okay? So we have another result. I am not sure if it is more general, in fact, but in any case.
Question about the previous theorem.
Yeah.
Maybe could you show a very simple example illustrating all of the points in the theorem?
A very simple and a particular example of what you mean?
Yes.
So the idea, I don't have a really particular example, but I can give you that the idea of this theorem is the same, that you have, if you have a definable group, that will be so definable inside a group quasisample, that will be definable with the automorphism and with the derivation. That means that, in fact, maybe you cannot understand the theorem, the group in general, but you know that there is a big part of this group who is really similar to the simple group, okay? So that means that in particular, there is a big part of this G0 that will be more or less isomorphic to the rational points of the simple group. And the idea is that you understand a big part who will be in some way similar to the rational points of a nice group, in particular an simple algebraic group. But a particular example, I am not completely sure how to do that. Yeah.
May I ask, following up on Alexi's question, are you allowed to use sigma to be the identity?
I am allowed to use what? Sorry?
Sigma to be the identity.
Yeah. So in that case, this doesn't. Yeah. When sigma is, that will be an automorphism, and that can be the identity. Yes.
Okay. So in that case, if you go back a couple of slides, when you define, when you define the sigma GN tutor, right? Then this would be just the a kind of diagonal. I mean, first of all, the H of U. I'm sorry.
That would be kind of trivial. Yes. Because,
it would be just kind of a diagonal. Is that correct? Some kind. I mean, this thing is just a product. This is just a product of H of U.
Yeah. All these fields are. All these fields. Yeah. All these fields are isomorphic to
HU itself, right?
Yeah.
So you would have an n+1 product of H of U. And so what are these then? These, could you use that as an example and just go through the couple of slides?
Before? Sorry, what do you say?
So assuming sigma is the identity, can we go through the slides quickly to see exactly what's going on in that case, in that very simple case?
In the case that sigma has an identity, so you will have here all the possibilities for, maybe 2 copies, 3 copies, and all copies that you want, because everything that will be H of U.
Right.
And you have the same here. So
no, Sami, if it's the identity, it's not coincidence. You're really using that it's a generic automorphism.
Yes, of course. Thank you.
Okay. What has to be coincidence? G has to be coincidence, right?
Yeah. That
Unique.
is part of our hypothesis.
You want
yes.
you want the diagonal map to be Cauchy dense, and
Yeah,
that can
yeah,
only
yeah.
happen if the automorphism is
Yeah,
generic.
yeah, yeah. I have the hypothesis that that we have something who is Cauchy dense, of course. Yes. Yeah.
Okay, all right.
I
So that
What-
doesn't apply, you're saying that? no?
Yeah. Sorry. You're right. So I was lost where we were. Yeah. So the idea is that maybe it's not a more general result, but now we want to, and I will maybe go fast in that. So the idea is that we want, now we understand what happened with definable groups inside a simple group. And that was our result. And now we want to prove, and we will to prove that some particular groups who maybe you don't know that are inside a simple group, but for some particular group you can find a simple group and you can apply these results. For that, I need this definition that we call definable quasi-sample. So if G is a definable group, G is definable quasi-sample if G has no abelian subgroup of finite index, and if whenever H is a definable infinite subgroup of G of finite index, so the normalizer has also infinite index. So if you have a subgroup who has infinite index, so the normalizer has infinite index. And we prove this theorem that say that, in particular, before that, this is a nice property because of this lemma in particular, because this property of the definable quasi-sample is a property that comes from the subgroup of finite index. So if you have that G is a group and G0 is definable subgroup of G of finite index, and if you take that passes also to the quotient, so if you take zeta finite normal subgroup of G, so G is definable quasi-sample if and only if G0 is definable quasi-sample, okay? And also if G is definable quasi-sample, if and only if the quotient that will be also definable quasi-sample. So those is a notion that go to the subgroup of finite index and also to the quotient. And in fact, this is I think not important. Just to remember that when I say you have this notion of algebraic group, you can have the same in the case of differential field. So just to be sure that when I say a delta algebraic group is this notion of algebraic group and now in differential algebra. And for elimination of quantifier in DCFM, we know that they are closely related to definable group in particular. But why I say that, and also in the same of delta simple, if you have a delta algebraic group with delta simples, when I say delta simple, it translates the notion of simple, but now for the differential case, if G is not commutative and has no proper connected normal delta closed subgroup. So what is the first the theorem that we prove? So we have this group just definable in U, but now that we know that is definable quasi-sample, so this definition that I just give you. So in that case, we can find a definable subgroup G0 finite index of G, so a big part of G, and also a delta simple group H. So and also a definable homomorphism between G0 and H of U with finite kernel and Cauchy dense image. Okay. So the idea is in the case that we know that G is definable quasi-sample, so you can find this H that will be really sample in the same of delta sample. It's a nice group. And we understand, we know that a big part of G that will be really similar to H of L, to H of U. Some ingredients of this proof. So the proof is really easy. In fact, it's a direct application of a result. Well, the first part is a direct application of a result from Blossier and Martin Pizarro that says that there was a result from 2015. The result from this, from Blossier, Martin Pizarro, and Frank Barner, that was so general, okay? So this is an application of this result for our context. The idea is that we know, and this is not, not something trivial to define, but it doesn't matter, but we know that DCFMA, it's something that we call one base over an omega stable theory DCFM. So it doesn't matter of that, but the idea is that the result of OR that was really, really general for theories that in general that satisfy where one base over some particular stable theory. But in any case, if you apply that to our context, they show that in fact, there exists a definable subgroup of G, G0. And also they find our delta algebraic group, because that would be, but not sample. So that would be a group who will be definable in the theory over such that was one base. So we find this, they find this H, that would be delta algebraic, and the isomorphism between G and H of U with finite kernel. Okay, so we know that they prove that in that case, there is a big part of G, G0, who will be inside this H of U. But the problem is that this H is just a delta algebraic. But using the fact, for this, we don't need the hypothesis of definable quasi-sample. But now we use the hypothesis of definable quasi-sample, and we prove that, in fact, we can suppose maybe the H is not delta sample, but you can change the H, and you can suppose that H that will be delta sample, okay? So we put these two results together, our first result and this result, and we obtain this theorem, okay? So in fact, this is not a strong result, it's just another result, okay? So this is just put the other result and this result together, and we obtain that in the case that G is an infinite definable subgroup U of DCFM of DCFMA, that means, remember, you have the derivation of the automorphism, and this is infinite and this is definable, and now we suppose that it's quasi-sample. So in that case, we can find the algebraic group. So we can find this group who is really nice, who is algebraic, and we can put this group inside this group, okay? So there exists this H that will be an algebraic group definable over the rational and definable subgroup G0 of G, finite index, and also a definable group homomorphism between G0 and H of U. We have the following properties. The kernel is finite, and this is the conclusion of the first theorem. So the Colchian closure of the image of G0 is it's isomorphic to H of L for some L who will be delta definable. In particular, that would be a constant field. And also we have that the image of G0, so G0, it's equal to H of L, or that will be definable inside and the rational points of L intersections on power of sigma. So it's just to put the two things together, okay? So, and now we have, this is the study when we want to understand definable groups inside a simple group, or in the case that we have that are definable quasi-sample. What happens if we want to do something a little bit more general, for example, for the semi-simple case, and I am not sure if I want to tell you that. It's kind of technical, the result, but the idea is that we can generalize that, but in the case that we are not simple, but semi-sample, we pick this result. In the case we use it, the same strategy. So we use the Cassidy result. Cassidy has another result for the case of semi-simple too. So, so we obtain something like that, that I don't want to explain you. The proof of that is much more technical than the other one. In any case, much more longer. But the idea is that you have our definable subgroup, and you take H that is semi-sample, and you suppose that G is also Zarinsky density H and also is definable inside H of U. So in the case that the sigma delta closure of G is connected for the sigma delta topology, so the idea is that you will find some particular simple normal groups of H, and a projection between our semi-simple group and the product and the product of the simple group that restricts as an injective map. And the idea is that you will find for each simple group, so you will find your definable subgroup G of I and Gi of prime of H of Li. So inside the simple group, of course, here we will use our order result. And we will prove in the end that that will be the image from this pi of G, not exactly the image, but some conjugate of this, that will be inside the product of the definable groups G of I and G prime of I. And remember that these all definable groups are definable inside a simpler group, okay? So, and we prove that in fact, we can suppose that this G, that will be normal subgroup of finite index, the left side, that will be normal subgroup of finite index of Gi of prime. And in particular, when you have that G is sigma delta closed, we know that that is exactly the image of G, well, some conjugate of that will be exactly the product of the G's, such that these G's that will be equal to HI of Li for some Li definable, or that will be defined, or a GE that will be defined inside this HI of Li for a formula that it's really similar to the other one. I really don't want I am not sure what I decided to give you this theorem, because it's kind of technical, but the idea is that we can have something similar in some way for the definable groups in the case of semi-sample. And so I think I finished here, but maybe we can speak a little bit in the second part, why, if we can do or not something similar when you have more automorphism.
Thank you. So let us thank Samaria.
Yeah, may I
Yes.
continue with the question? So I'm going back to the slide where you define H subscript bracket N.
When you define what?
When you define the H sub bracket N.
The prolongations.
I don't know the page number.
Yeah.
Anyway.
That's one. Yeah.
Yeah, right here, right. Okay, yeah. Okay. Now here you say, so I'm still thinking that sigma is the identity, and then you say, so we have that. This is quotient dense. Now, is that a conclusion or is that a hypothesis?
For that case, this is where you say that. So we have the Pn of A.
Yeah.
No, that's a conclusion.
It's a conclusion. So, but it is not. You just told me that it's not true when sigma is the identity.
We have the hypothesis here that looking at here. Sorry, I am confused now. So we have here that has Pn of H is coaching das. Yeah, because in the other case, I really suppose that we are Zarinsky dense. I am here. What happened with the identity?
So if sigma is the identity, it's not quotient dense because then
Yeah,
right.
No, it's not
just
true.
a diagonal.
Yeah.
Right. So when you say this,
In that case, no, yeah, you are right. Yeah, you are right. So
when you say,
not true
I
in the
don't
case
know
that
whether you have to suppose that that this is the case because of H is very special, or what?
No, it's because you're working in a model of DCFMA, and that forces the automorphism to behave generically with respect to the derivation.
exactly.
That forces the what?
That the automorphism is generic. Remember that the rational points here are in the
monster model, right?
Yeah.
So
Sorry.
so why? But what has that to do with H?
I am not completely sure of your question, so I may be confused. So I'm not completely sure of your question. I think I am confused.
If I may, sorry to barge in again. So what's H? Well, there's no. You don't need anything about H. What you need is the fact that you're a model of DCFMA,
Right.
which forces something about the automorphism.
Yeah.
So the automorphism is special, not the group.
Yeah. So the H is an algebraic group, but we take the product between the rational points of a model of DCFMA.
So, Will, I think part of the axiom of DCFMA gives you that conclusion.
Yeah. It's not only because we need the fact that U is not a field, it's a field who is a model of DCFMA. Yeah.
So the question still is, can we use sigma equal to identity in DCFMA?
No. So
No.
Or is there? So you're saying that there's no monster model
In that moment.
if sigma is
Yeah, exactly.
Is that right then?
it's not going to be a model of DCFMA.
Of DCFMA. Yeah. This is the thing.
Right. So when sigma is identity, there's no unit, no monster model.
Exactly. That. Yeah.
Okay, all right, thanks then.
Are there any other questions? So I have one, but I guess I'll keep it for kickstarting the next session. So if we don't have any other question, let us thank Samaria again. And so I'll stop the recording now.